Satellite, Spartan Halley experiment. And here comes the flight crew now. Commander Dick Scobie, followed by Mission Specialist Judy Resnick, Ron McNair, and pilot Mike Smith, followed by Krista McCullough, teacher in space, Ellison Onizuka, and payload specialist Greg Jarvis. Big smiles today. Confidently getting into the van. They're going to go up to that pad and attempt a second try. Second try at launch today. It'll take a few minutes for the astronaut van to get to the pad.
Worked as a senior systems engineer in product development for the Xerox Corporation in California. She's a native of Akron, Ohio, and also a classical pianist, and enjoys flying and bicycling in her spare time. Ellison Onizuka also in the White Room. Actually, everybody's going to be in there shortly as they get ready. The teacher observer, Krista McAuliffe, has been handed an apple by the closeout crew. Ellison Onizuka now getting his egress harness on. The native of Hawaii is a graduate of Kona Wai'ina High School and earned both a Bachelor and Master of Science degree in aerospace engineering from the University of Colorado. After receiving his commission in the Air Force, he served as a flight test engineer and participated in the flight programs and system safety engineering for a wide variety of aircraft. He graduated from the Air Force Test Pilot School and then served on the staff. Onizuka is one of the astronauts known as the Cape Crusaders, who were assigned to KSC for a period of time of several launches and work with the orbiter test and checkout teams and the launch support crews. The astronaut support person on board, Sonny Billy Bob Carter, is also one of the Cape Crusaders at the present time.
Go ahead, LPS. Go ahead, LPS. Go ahead, TLS.
TLS functional initialization is complete. That's step 405.
405, copy. Go ahead, TDSA.
Roger. We're going to not perform 0535 and 0536.
Copy that, thank you.
Good morning.
OVCC, OTC.
Go ahead.
Okay, apparently one of the crew left their gloves in the Astrovan.
Between the orbiter, the firing room here at Kennedy Space Center, and Houston. Booster engine gimbal now underway. T-minus 15 seconds. T-minus
10 seconds.
10,
Let's go for main
9,
engine start.
8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Now control program. Roger, roll, Challenger. Good, roll program confirmed. Challenger now heading downrange. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles. Engines throttling up, 3 engines now at 104%. Challenger, go at throttle up. Challenger, go at throttle up. One minute, 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles. Flight controllers here looking very carefully at the situation. Obviously a major malfunction. We have no downlink. We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that. We are looking at checking with the recovery forces to see what can be done at this point. Contingency procedures are in effect. We will report more as we have information available. Again, to repeat, we have a report relayed through the flight dynamics officer that the vehicle has exploded. We are now looking at all the contingency operations and awaiting word from any recovery forces in the downrange field.
The fueling of the external tank began at 1:25 a.m. Ice had accumulated on the launch pad during the night. Several water systems were opened slightly and allowed to flow into drains. The drains froze and caused overflows. High wind gusts spread the water over large areas and ice formed. The air temperature at launch was 36 degrees Fahrenheit. This was 15 degrees colder than any previous launch. At T-minus 7 minutes and 30 seconds, the ground launch sequencer began retracting the crew access arm. The arm can be put back in place within 15 to 20 seconds if an emergency arises and the crew must evacuate the pad. At T-minus 3 minutes and 15 seconds, gimbal checks of the orbiter main engines were performed. All 3 engines move in a pre-programmed pattern to verify ascent flight control. The gimbal sequence ends with the engines in their start positions. At T-minus 2 minutes and 55 seconds, external tank liquid oxygen pressurization began and main engine purging was completed. At T-minus 2 minutes and 50 seconds, retraction of the gaseous oxygen vent hood began. The ground launch sequencer verified its full retraction at T-minus 37 seconds. Sound suppression water was started at T-minus 16 seconds. At T-minus 8 seconds, hydrogen igniters were turned on to burn off any free hydrogen. 6.6 seconds before launch, Challenger's liquid-fueled main engines were ignited in sequence and run up to full thrust. Thrust from the main engines bends the shuttle stack. When it returned to vertical, the solid rocket boosters ignited. At T0, the hold-down bolts were explosively released. After the initial pre-release twang motion, structural forces on the assembly are dissipated through vibration at a rate of 3 cycles per second during the first few seconds of flight.
Space shuttle mission, and it has cleared the tower.
Roll maneuver was initiated at 7.724 seconds. The maneuver was completed at 21.124 seconds.
Normal throttles for most of the flight, 104%. We'll throttle down to 65%.
The main engines were throttled back to 65% at 35.379 seconds for about 16 seconds in order to alleviate loads during maximum dynamic pressure.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3.
The engines were then throttled up to 104% at 51.919 seconds.
3 engines now at 104%.
Challenger, go at throttle up.
During the flight, telemetry data gave no indication of problems.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
The solid rocket boosters continued in flight and were destroyed by the range safety officer 110 seconds after launch. This graphic indicates viewing angles for 3 cameras in the vicinity of the launch site. The first view shown is from camera E63 at the lower right of the chart. At 0.678 seconds into the flight, a strong puff of gray smoke can be seen spurting from the vicinity of the aft field joint on the right solid rocket booster. The vaporized material streaming from the joint indicates there was not complete sealing action within the joint. This second view is from camera E60. The smoke can be seen between the right SRB and the external tank and initially moves in the upward direction. The angle between this view and E63 is approximately 100 degrees. With E60 and E63 side by side, it is clear that when smoke is first visible to camera E60, it is not yet visible to E63. 0.2 seconds later, it becomes visible to E63 and is seen in multiple lobes, or puffs, reaching maximum visibility at about 1.9 seconds. A third, higher-resolution camera, D67, was located east of the launch pad. D67 recorded this view of the smoke at approximately the same time of maximum development. Smoke appears to the right side of the SRB only, while normal water condensation vapors appear to the left. This plan shows that none of the cameras directly view the surface of the right SRB in the shaded region of the graphic. Analysis of film from several pad cameras indicated that the smoke came from between 270 and 310 degrees on the circumference of the aft field joint. As indicated on these pre-flight photos, the smoke emerged from just above the strut, between the SRB and ET, at a point along the longitudinal axis near the aft field joint. The multiple smoke puffs occurred at a rate of about 4 times per second, approximating the frequency of the structural load dynamics and resultant joint flexing. This greatly exaggerated computer animation depicts the flexing of the SRB joint. This flexing increased the gap between the tang and clevis at the location of 2 rubber O-ring seals. Last evidence of smoke above the aft attach ring appears at 2.733 seconds. The last indication of smoke dispersing below the aft dome appears at 3.375 seconds. Film records of the assembly of the solid rocket booster were reviewed to determine any evidence of cause for the smoke. Photographs taken just prior to mating of the booster segments at the aft field joint show the O-rings installed in the grease clevis grooves. A subtle variation was detected, but through computer enhancement was determined to be a shadow caused by irregularities in the grease. No evidence of O-ring defects was observed in any of the stacking photography. The facility gaseous hydrogen vent arm was not captured after retraction at launch. Film analysis, however, showed that it did not rebound and contact the vehicle or contribute to the accident. Post-launch inspection of the hold-down posts revealed that the kickspring assemblies on 4 of the posts were missing. Detailed analysis determined that the assemblies could not have become detached prior to T plus 850 milliseconds and were not a contributing factor to the smoke observed at liftoff. The next significant event was the development of the SRB burn-through plume. Camera E207, located about 6 miles north of the launch pad, shows the growth of this plume. The first evidence of flame appeared on the right solid rocket booster at 58.788 seconds. This occurred as the main engines had been throttled up to 104% thrust and the SRBs were increasing thrust. Camera E203 was located west of the launch site and gives an aft view. The exposure was set for the booster nozzle plumes. This graphic illustrates the location of the flare. The flare was located near the aft field joint, approximately 300 degrees circumferentially, which is consistent with the location of the smoke emissions at liftoff. Within half a second, the flame had grown into a continuous and well-defined plume. At about the same time, telemetry showed a divergence in chamber pressures between the right and left SRBs. Pressure in the right SRB chamber was lower as a result of the growing leak. The plume is seen here impinging directly onto the surface of the external tank and the lower aft strut at 60.248 seconds. At about 62 seconds, the control system elements began to respond to the forces caused by the plume. As recorded on E207 and E204, the first visual indication that the anomalous plume penetrated the external tank was seen at 64.66 seconds as an abrupt change in the shape and color of the plume. This is an indication of hydrogen leaking from the external tank. At 64.705 seconds, a bright sustained glow developed between the orbiter and the external tank. Slight changes in the hydrogen tank pressure telemetry data confirmed the leak 2.2 seconds later at 66.8 seconds, when the LH2 tank pressurization system could no longer maintain its normal repressurization rate. At 72.6 seconds, the LH2 tank pressure could no longer be maintained, indicating that the leak path had significantly increased and was growing rapidly. At 72.2 seconds, the guidance system showed that right SRB motion diverged from the orbiter and left SRB, indicating that the lower ET SRB strut was severed or pulled loose. During this time frame, exaggerated steering commands and control system responses registered in telemetry data. At approximately 73 seconds, both liquid hydrogen and liquid oxygen pressure to the main engines showed a significant drop. This was followed at 73.124 seconds by the appearance of a circumferential white pattern around the ET aft region, suggesting LH2 tank structural failure. 13 milliseconds later, at 73.137 seconds, vapor was observed at the inner tank, indicative of the liquid oxygen tank failing. This can be attributed to abnormal loads induced by either the right SRB rotation at the forward attach point or the propulsive forces created by the LH2 tank aft bulkhead failure, probably both. Within milliseconds, liquid oxygen was observed streaming along the external tank. At 73.191 seconds, a flash was observed between the ET and orbiter that was immediately followed by the start of total vehicle breakup at 73.213 seconds. During the next 100 milliseconds, additional flashes occur in the SRB forward attach area. As the ET broke up, the released fluids vaporized rapidly, producing an expanding cloud of gases, vapors, and cryogenic fluid with embedded debris and localized combustion of mixed gases. No shock wave or other evidence of a violent explosion was detected in the imagery. Illumination from a combination of SRB plume radiance, reflected sunlight, and peripheral burning of gases gives the cloud the appearance of a fireball. By 73.6 seconds, the main engines were in automatic shutdown mode as a result of reduced propellant pressures. The last telemetry from Challenger was received 73.618 seconds after launch. The actual vehicle breakup was essentially obscured from view by the vapor cloud which abruptly enveloped the vehicle. Hundreds of fragments were noted exiting the ET cloud. Those identified included the shuttle main engines, the left wing, crew cabin, and both SRBs. Approximately 1 second after initial breakup, film showed the front segment of the orbiter emerging from the cloud. The nose, crew cabin, and a portion of the cargo bay make up the orbiter in this view. Nitrogen tetroxide oxidizer from the forward reaction control system provided a distinctive orange-brown color to the cloud. By 74.578 seconds, a yellow cloud or flash was visible near the orbiter nose segment. This is believed to be caused by burning monomethyl hydrazine from the forward RCS. The flash reaction from the RCS propellants abated, revealing separation of the nose section from the crew cabin. Less than a quarter of a second later, the crew cabin was noted to be severed from the cargo bay. Igniting of propellant discharge continued to be observed from the forward RCS. A camera south of the launch pad recorded a wider array of debris exiting the vapor cloud. The initial emergence of the crew cabin from this perspective was at 75.237 seconds. The initial path of the crew cabin from the vapor cloud carried it across the path of an adjacent contrail, clearly revealing its truncated form and attitude. The left wing became visible at 78.531 seconds. The main engines and crew cabin are also identifiable. After 10 seconds, the crew cabin was seen again with the front end and top of the cabin visible. As the subject moved further away and dropped lower on the horizon, the quality of the image for visual analysis deteriorated rapidly. Long-range tracking cameras followed the SRB's through-range safety destruct. At approximately 75.8 seconds, the right SRB was seen exiting the cloud. Camera E207 shows the right SRB after the breakup, and the joints are clearly visible except for the aft field joint. This confirmed the location of the plume along the longitudinal axis of the SRB. The separated nose cap and deployed drogue parachute are identified at approximately 76.4 seconds. The shock wave from the detonation of the linear-shaped charge on the right SRB can be seen clearly. Simultaneously, the left SRB was destroyed.
Mode. Coming up on the 30-second point in our countdown. T-minus 30 seconds, and we've had a go for auto sequence start. The SRB hydraulic power units have started. T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1. And liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Pieces of ice tumble off as the coldest Space Shuttle launch ever gets underway. Challenger seems to shake herself free of the ice and goes. All 5 rocket engines burning well. The first teacher, Christopher McAuliffe, on her way to space with 6 other astronauts on board.
Engines beginning throttling down now.
Charlie from John Lawrence in Houston.
Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly.
Straight up into a beautiful blue sky, crystal clear weather here in Florida.
65%. 3 engines running normally, 3 good fuel cells, 3 good APUs.
Everything going well.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles.
And across from me, hundreds of school kids jumping up and down and cheering as this space shuttle takes off with teacher Christopher McAuliffe on board.
Go and throttle up.
And that means the engines are running well. 2.5 minutes into the flight, the solid rocket boosters will drop away, and we should be able to see it. What's happened?
Feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Still going. Vic, did something strange happen then?
Something is gone amiss.
Something is wrong. We have a problem.
Nothing from mission control, but I could see pieces of something falling off the side as if one of the solid rocket boosters had come away early, Bob.
It's still climbing. The shuttle is still climbing, but there is a problem. There appears to be a serious problem. What's happening?
Not a word from mission control. Everybody here is open now.
Controllers here looking very carefully at the situation.
Where is the shuttle, Vic? Can you see it?
Major malfunction.
There is
Obviously
a major problem.
malfunction. Something has gone
This
seriously
could be a
wrong.
major tragedy.
We have no downlink.
A major tragedy in the making in this shuttle mission.
We have no downlink is the word from Mission Control. Something has gone gravely wrong, and the shuttle itself
It's disappeared,
has not been heard from. Disappeared in a cloud of smoke about a minute
Now
and a half into the launching.
I see a very thin contrail, Vic, on the NASA monitors. This is indeed a tragedy. There appears to have been an explosion. Something is wrong. We see contrails dropping. Nothing from NASA.
And no comlink from the shuttle, and no word from the telemetry that tracks the shuttle's progress.
We have a report from the flight dynamics officer that the vehicle has exploded.
We have a major tragedy.
We are looking at checking with the recovery forces to see what can be done at this point.
My God, a major tragedy. The shuttle has exploded. The Challenger has exploded.
Contingency procedures are in effect. We will report more as we have information available. Again, to repeat, we have a report relayed through the flight dynamics officer that the vehicle has exploded. We are now looking at all the contingency operations and awaiting word from any recovery forces in the downrange field.